So first of all, some definitions which hopefully we know. Radius. So technically a radius is any interval that joins the centre of a circle to the circumference. Well, that's the formal definition of radius. Diameter then is an interval which passes through the centre and joins 2 points on the circumference. So thus meaning a diameter is made up of 2 radii. A chord is any interval that joins 2 points on the circumference. So it doesn't have to pass through the centre, meaning the diameter is also a chord. It's just a special chord that passes through the centre. A secant is not an interval, but a line. So it extends through the circle. So a secant doesn't stop at the circumference. So it just cuts the circle, any line that cuts the circle. Tangent, well, hopefully we know that one. That's the line that just touches the circle. So it doesn't actually go inside the circle. An arc is just a piece of the circumference. Mind you, when I label an arc, I actually create 2 arcs. We have the minor arc is the smaller piece, and the major arc being the larger piece. So a sector, so its boundary it has 2 radii and an arc. Again, I've labelled the minor sector, but of course the other bit is what we call the major sector. And some people like to think of it as the piece of pie, and the major sector is when you're greedy. Now, a quadrant. So that's a sector where the angle at the centre is 90 degrees, thus getting a quarter of the circle. So quad being the prefix meaning 4 quadrants in a circle. Segment, that has a boundary of a chord and an arc. And again, we have a minor segment and a major segment. Now, a semicircle would be a segment, but it also would be a sector as well. It satisfies both definitions, but it has its own special name, semicircle. Concyclic points. So points that lie on the same circle. There we go, so A, B, C, D are concyclic points. Now these 4 points will create what we call a cyclic quadrilateral. So any quadrilateral whose vertices lie on the same circle is a cyclic quadrilateral. Now what I've just drawn there, that angle alpha is the angle subtended at the centre by the arc. So to subtend an angle means 2 points will always subtend an angle at a third point. So in this case, the third point is the centre of the circle. We've got 2 points A, B, joined them up to a third point, and that's what's called subtending an angle. Now, when I say arc AB, I'm talking about the minor arc AB. The reflex angle is subtended by the major arc AB. And that would be an example, beta would be an example of an angle subtended at the circumference. So we're joining it up to the circumference, and you might remember we actually have a theorem relating those 2 angles, which we'll look at later. Concentric circles, circles that have the same centre. This diagram is an example of 2 circles that touch internally. Okay? So if they touch internally, basically they'll have a common tangent at the point where they touch. As opposed to this next diagram, they also touch, but they touch externally. They still have the common tangent. So 2 circles touch internally versus 2 touching externally. Let's look at our initial theorems. Chord theorems, which you'll notice I've put in brackets or parentheses there, arc theorems, because often you can swap the word chord with arc on these theorems. So let's have a look at the first one. Oh, not so much a theorem, but something to remember, and you can use it. Equal chords will always cut off equal arcs. That's why sometimes we can swap the word chord with arc, because they'll have the same endpoints basically. So you could join them A to B, it would be a chord, or you could go around the circumference and it would be an arc. But you still got the same two endpoints. Alright, so the first theorem. Perpendicular joined to a chord from the centre of a circle bisects the chord, and the perpendicular bisector of a chord will always pass through the centre. Well, what are we talking about? Let's draw a diagram here. So it's this situation, and what I'm saying is, if I know that this line from the centre is perpendicular to the chord, then it must cut the chord in half. That's what we're basically saying. So the fact that I know is that that line is perpendicular. From that I can say, well, AX must equal BX. Reason, the perpendicular from the centre will always bisect the chord. Let's prove it. And a lot of these circle geometry proofs just use congruent triangles. So what do I know? I know AB is perpendicular to OX. I want to prove that AX is equal to BX. Okay. Well, if I join up two radii there to create some triangles, so I've got AO and BO, they've given me that is 90 degrees. Okay, so I've got 90 degrees in both triangles. Well, AO and BO are both radii, so they're equal in length. And OX is common. Right angle, hypotenuse, side. So I now know those two triangles are congruent. If they're congruent, I can say, well, AX and BX would be the matching sides in congruent triangles. Now, of course, that's the proof. You don't have to do that every time. We just quote the proof. Okay, there we're playing footsies under the table. So the reverse of number one. So the first one was we knew they were perpendicular and we could say, well, therefore these lines were equal. But the other way works as well. If we know that they're equal, then we can say they're perpendicular. So this time what I know is AX is equal to BX, so then I can conclude that they're perpendicular. So I can say, well, OX is perpendicular to AB, because I know the line that joins the centre to the midpoint will always be perpendicular to the chord. Let's prove that one. And once again, I'll do it via congruent triangles. So let's join in those two radii to create a couple of triangles. And this time I've got AX equals BX, given information. The equal radii and the common side, I've got side, side, side. So they are congruent, meaning that AXO and BXO must be the same size. They're now matching angles in congruent triangles. But I also know they add up to 180 degrees because they lie in a straight line, so they're straight angle. Well, logically then AXO must be 90 degrees. Equal chords are the same distance from the centre and subtend equal angles at the centre. There's my diagram, there's my diagram. So what we're saying is we know AB and CD are the same length. What can I conclude from that? I can conclude that OX is equal to OY. Equal chords are equidistant from the centre. I can also conclude that angle AOB will equal angle COD. Equal chords subtend equal angles at the centre. Now this is one of the ones where I might use the word arc instead of chords, because equal arcs will also subtend equal angles at the centre. Because if I'm subtending an angle, remember what I said it was? 2 points joining up to a third point. Well, it doesn't matter whether I'm talking about the chord or the arc, it's still the same two endpoints that I'm joining up to the centre. So equal chords or equal arcs, it doesn't matter, subtend equal angles at the centre. Alright, let's prove it. So we know AB is equal to CD, we've been told that. I know that OX is perpendicular to AB and OY is perpendicular to CD. We're going to prove that those distances are the same. Again, I'm going to create some triangles. So I'm going to draw in two radii. AB is equal to CD. They were the equal chords. That's what's given to me. Okay, so from there, I'm going to conclude that AX is half of AB. Perpendicular from the centre, bisects the chord. do the same with CY. CY must be half CD. But hang on, we said AB was equal to CD, so therefore AX must equal CY. Alright, so I've got a side in each of these triangles being the same. AXO is CYO is 90 degrees, that was given information. So I have a right angle. I have the equal radii, that would be the hypotenuse. I can use the right angle hypotenuse side proof. Okay, I now know they're congruent. So I can say, well, OX is equal to OY. Matching sides in congruent triangles. Now the angle one. So this time, I know AB is equal to CD. This one's a heck of a lot easier. Because all I want to do is prove angle AOB is equal to angle COD. Well, we've been told AB is equal to CD, and everything else are radii. So AO equals BO equals CO equals DO. Remember, in geometry, it is okay to have several equal signs on one line, because we're saying, hey, all these things are equal. It's not like an equation. So they're equal radii. So we've got side, side, side. And so we then have matching angles in congruent triangles. Okay, there's some initial theorems to get started with. As I say, you don't have to prove those theorems. Fortunately, we can just use those theorems to go and solve some of the problems.